Rhythm that involves the natural log, and I just want to be clear, by the natural log of x. Now a lot of people drop the parentheses. I don't like doing that because it is a function, but the natural log of x is actually equal to log base e of x. Log base e. Now sometimes when you're working these problems, you don't really even need to know, you know, the properties are so formal, it's hardly, sometimes the base really isn't relevant. And that's actually the case here. Now also, you might think that you can use this property of logarithms that goes like this. It's kind of an illusion though. Natural log of a over b. Notice this is just the natural log of the quotient, which is not the form that you see as far as the problem we're trying to solve. So this well-known result for a logarithm to any base due to laws of exponents is just equal to the difference of the log of the numerator. Okay. ln a this time I'll break my own convention just in the name of brevity. Ln a natural log of a minus the natural log. Now I'm taking the time to write this down because myself and others I know have been tempted to use this, but it's not really applicable. Right, folks? In other words, this looks like it might apply here, but really on closer inspection, you have two occurrences of the logarithm function. One in the numerator, one in the denominator, which is not the case here. You just have the log of a quotient, right? Now this is a quotient, but it involves two logarithms. So this rule right here, while true, is not applicable, okay? Now, so what we do is we resort to the definition of a logarithm. In other words, the natural log function is a base e function, and every logarithmic statement has a corresponding exponential. You can think of exponentiating both sides of this. And also just a more natural believability test on this would be, say, consider log base 10 of 1,000. Okay, well, log base 10 of 1,000 is equal to 3 precisely because 10 raised to the third power is equal to 1,000. And that's the same thing right here. We're just using this transcendental base here, e. Okay? So in other words, this is the definition of the logarithm of this number and this number on consecutive lines. All right? Now let's keep going here. Now, we are trying to figure out, I mean, if we can figure out what A and B are, you know, or a relationship between A and B, we'll be done with the problem. So let's just go ahead and multiply them together to take advantage of properties here, properties of exponents. And also notice that this is A plus B. This is in the form A plus B. A plus B right here. And then, of course, this is A minus B. And this is a standard type of problem. It's kind of designed to work out nicely, and you'll see that in a moment. Okay, now, of course, over here, this would be A squared minus B squared. Okay, the well-known difference of two squares. It's used all the time. Okay, I still see people trying to expand this out and then they notice things cancel, but there's no need to do that. Now notice that if this is your B, 6 times 6 is 36, square root of 10 squared is 10, 36 times 10 is 360, you see right here? This is 361, so this is actually equal to 1. 19 squared is, and that's what makes this thing work out rather nicely. But there's still one little step we need to take. Okay, now notice we've shown that e to the a times e to the b is equal to 1, but also if you remember one of the properties of exponents, this is the same thing as e to the a plus b. Now I'll go ahead and put the parentheses, perhaps unnecessary, but that's e to the a plus b. Okay, but we've just shown that's equal to 1. But notice the only way any exponential can be equal to 1 is if this part is 0. So you see, this implies that, in other words, this expression here, e raised to the 0 power, is the only way this can be equal to 1, or any other base for that matter. And so this would imply that a plus b has to equal to 0. Yeah, I'm going to do my best to make a legitimate a. This is an a, not some. Okay, that's a plus b must equal 0. Okay, and again, folks, I hope that's clear, because that I'm just using, let me come up over here, anything, b raised to the 0 is equal to 1, right? And that's the only time the exponential is equal to 1. B raised to the 0 is always, I'm using a different, doesn't make any difference. Okay, b raised to the 0 for any base is equal to 1. So that's where we're getting that a plus b, this a plus b has to equal to this 0. That's exactly what we wrote down right here. Okay, now, so what does that tell us? That tells us that a is equal to negative b, always in this kind of setup. So a would be equal to negative b. Okay, we're finally going to get to the punchline here. Now, this is our original problem, and we already know, just based on the way we set this up, that the numerator is equal to a. Okay, the numerator is equal to a, just by our setup here. Right, and then the denominator is equal to b, right? So I just rewrote it down here. So what we get here is that this is equal to minus b over b. And that, of course, is equal to negative 1. So after all of that, folks, it just craps out into negative 1. All right, folks, that's it. And I thought it was kind of neat. We actually appealed. There's no nice properties of logarithms that's going to help us get through that. I think the only choice we have is to resort to the definition of the logarithm. There's all these rules, power rules, quotient rules, product rules, all this stuff. But in this particular case, none of those apply. And so you have to just go back to the definition of the logarithm. Alrighty, so anyway, that's about it. There's our answer. I hope you enjoyed.